Welcome back to this advanced manufacturing and process modeling course. So, we were discussing about the additive manufacturing and process modeling module. So, we have so far covered about the basics of additive manufacturing and also application of computational fluid dynamics based process modeling to grab insight into the heat and mass transfer and fluid flow phenomena involved in case of additive manufacturing. And also we have discussed briefly in the previous class about how microstructure modeling can play a big role to predict the anisotropic microstructural features that we generally come across in case of additive manufacturing, more importantly metal additive manufacturing processes. So, continuing to that, in today's class we will discuss further about how we can develop phase field based microstructure model to simulate the microstructure evolution mechanism process in case of additive manufacturing. And the basic principles has been have been covered already when we have discussed about the process modeling of casting processes. However, I will quickly go through about the fundamentals, the governing equations and all which are needed to be solved to to get the phase field simulation results of microstructure evolution. So, coming to the phase field model governing equation. So, free energy function F consists of interfacial free energy and chemical free energy. So, as you see, so this is basically the free energy functional capital F, and this is your FIF is the interfacial free energy component, and FCH is the chemical free energy component, and which can be expressed as FIF is equal to FIF, which is a function of phi alpha, that is the phase field variable, and FCH is the function of both phase field parameter as well as the phase composition field C alpha. Okay. So, so multi-phase field model, according to the principles of multi-phase field model, summation of phi alpha alpha is equal to 1 to n, that means summation of all the phase field parameters of different phases equals to 1, and we already know that phase field parameter assumes the value of 0 when it is in liquid, and it assumes the value of 1 when it is depicting solid. And so the composition term, which is a function of both space and time, composition gradient term, so which is C bar x t is equal to summation of alpha is equal to 1 to n phi alpha into C alpha bar. So, the basic equation relating the temporal variation of phi with the free energy functional F is the following. So, F phi alpha dot is equal to summation of beta not equal to alpha to n pi square by 8 eta n mu alpha beta into del f by del phi alpha minus del f by del phi beta, when there are two phases involved, that is alpha and beta, where mu alpha beta is the kinetic coefficient in Gibbs-Thomson equation, which is replaced by an effective mobility term m alpha beta, considering a diffused interface between the evolving phases or grains alpha and beta. So, we have already discussed about the concept of diffused interface between the liquid and evolving solid phases. So, phase field is based on a diffused interface approach. It does not consider a sharp interface approach. So, we are considering diffused interface. So, time evolution of the phase field order parameter can be expressed with this equation, where phi dot alpha is equal to summation of beta not equal to alpha to nu m alpha beta to the power phi into b delta g alpha beta minus sigma alpha beta k alpha beta plus a alpha beta plus summation of gamma not equal to alpha not equal to beta to nu j alpha beta gamma. So, what are these? So, then here as we already told that m alpha beta is the mobility term, and b delta g alpha beta is the chemical driving force, and sigma alpha beta into k alpha beta plus a alpha beta is the dual interface terms, and then the last one, that is j alpha beta gamma is the higher interface term. So, here alpha beta and gamma represents different phases. Nu represents the total grain count, alpha beta and alpha beta gamma are the interfaces between the alpha and beta phases, and triple junctions between the alpha, beta and gamma phases, and m alpha beta, as I told, denotes the mobility of the phase alpha beta interface, and sigma alpha beta is the anisotropic interfacial energy, k alpha beta is the pairwise curvature, and a alpha beta is the alpha beta interface anisotropy. So, mobility, if we can define mobility, that is m alpha beta mobility of the interface between phases alpha and beta, which can be expressed as this equation. So, that is mu alpha beta to the power g by 1 plus mu alpha beta to the power g eta del s. S is the entropy change on alpha beta phase transformation by 8. Summation of I m I to L summation of j d alpha I j minus 1 to the power minus 1 into 1 minus k j c j alpha. So, here eta is the interface thickness, delta s alpha beta is the entropy change on alpha beta fusion, and m I superscript L is the slope of liquidus line for component I. So, and d alpha I j is the basically the diffusion matrix for grain alpha, phase alpha. K j is the partition coefficient for pure materials, or for small eta, small interface thickness between the solid liquid interface thickness, m alpha beta becomes equal to mu alpha beta. Okay. And j delta g alpha beta, that is the free energy change, which is the driving force for the phase transformation, is equal to 1 by nu to the power m into del g del phi alpha minus del g by del phi beta, where nu m is the molar volume and g is the molar Gibbs free energy density. Okay. So, what is pairwise curvature? Pairwise curvature k alpha beta is determined using the following equation, that is k alpha beta is equal to pi square by 2 eta square into phi beta minus phi alpha plus half grad square phi beta minus grad square phi alpha. Okay. So, so the equation for high order triple junction term j alpha beta gamma can be expressed as this. So, j alpha beta gamma is equal to half sigma beta gamma minus sigma alpha gamma into pi by eta square phi gamma plus grad square phi gamma. And anisotropic interfacial energy sigma alpha beta is equal to sigma alpha beta 0 and alpha into a alpha beta to the power sigma n. So, anisotropic interfacial mobility m alpha beta phi is equal to m alpha beta phi a to the alpha beta, which is a function of unit normal. So, then n bar is the interface normal, and interfacial anisotropy term a alpha beta is equal to minus grad a alpha beta to the power sigma and a alpha beta sigma superscript again into grad phi beta minus grad phi alpha plus 1 by a alpha beta superscript sigma summation of I is equal to 1 to 3 grad I into del a alpha beta superscript sigma by del grad I phi beta minus del a alpha beta superscript sigma divided by del gradient of phi alpha, okay, into pi square by 2 eta square phi alpha phi beta minus half grad phi alpha into grad phi beta, where b is the prefactor which is calculated based on this expression. So, where b is equal to pi by eta into phi alpha plus phi beta into root over phi alpha phi beta. Okay. So, in case of sharp interface models, phases present within the computational domain remains independent to each other, whereas in case of the present phase field model, which adopts a diffused interface approach, wherein the interface is described as a mixture of overlapping phases. The below mentioned equation shows how the local concentration C, which is function of both space and time x and t at the diffused interface, is related to the phase concentration C alpha x comma t. So, C x t is equal to summation of alpha is equal to 1 to n, that means for n number of phases phi alpha x t C alpha x t. So, the set of diffusion equations, that is k diffusion equations for a total number of k components adopted in the present PF model can be represented by the following equation, that is C bar dot is equal to grad summation of alpha is equal to 1 to n phi alpha d alpha, d alpha is the diffusion matrix into grad C alpha bar. So, so the global temperature evolution of the system can be expressed as per this equation, that is T dot, that is dt dt, so that is evolution of temperature with respect to time is equal to 1 by Cp bar, that is the average Cp, average specific heat, constant pressure specific heat averaged over the cells of the numerical grid n x y z. So, into 1 minus q dot by v dt plus summation of h alpha f alpha dot. So, where q dot by v represents the rate of heat extraction from the computational domain where the microstructure modeling is being performed per unit volume. So, H alpha is the enthalpy per unit volume of phase alpha, Cp bar as I told earlier is the average specific heat averaged over the cells of the numerical grid having n number of cells, and f alpha dot represents the average rate of change of phase alpha. Okay. So, now to if I take an example of our research work from our own group, so which shows you that so these are the parameters considered for the simulation purpose, that is laser power of around 310 watt, scanning speed of 1000 millimeter per minute, layer thickness of 40 micron. So, this is a typical example of laser powder bed fusion, and laser spot diameter of 0.08 mm, recoater speed of 150 centimeter per second, and particle size in the range of 20 to 40 micrometer. So, the chemical composition of IN 718 superalloy is this, which is considered for this case study of microstructure modeling during laser powder bed fusion of 3 layer model. So, you see that each layer having thickness of 40 micrometer. So, when the second layer is deposited on top of that, it becomes 80 micrometer, and finally, when the third layer is deposited, the domain size becomes 120 micrometer. Okay. So, the phase interactions, boundary conditions, nucleation conditions, temperature evolution have to be chosen properly to simulate the microstructure evolution in the laser powder bed fusion of this particular nickel based superalloy. So, insulating boundary conditions are chosen here in the computational domain in top and bottom to achieve the grain growth from bottom to top direction. Okay, because bottom is the chill zone, bottom layer is above the substrate plate, which is which is at a much lower temperature, close to room temperature, and the top layer of the powder bed, which is under immediate exposure to the laser beam. So, that there the temperature is high. So, temperature gradient acts here from bottom to top. Okay. So, the boundary conditions considered in this typical domain. So, the domain is shown over here. So, this is your computational domain. So, here for both phase field and concentration field are the following, that is west and east is the periodic and bottom and top insulated. Okay. So, so this is a typical simulated micrograph which is shown for the case of first layer having 40 micrometer height and 10 micrometer width. Okay. So, so it is basically it is the simulated micrograph shows the niobium distribution map. So, why niobium? Because niobium is getting segregated into the inter dendritic spaces because of the evolution of the gamma dendrites. So, as we have discussed several times earlier, here the morphology of the evolving dendrites depends on the G by R ratio, that means thermal gradient divided by the solidification front growth velocity. So, as we also discussed earlier that based on G by R ratio, the microstructure transitions from planar at a very high G by R ratio to your cellular, and then from cellular if with further decrease of G by R ratio it transitions to cellular dendritic, and then if there is further reduction of the G by R ratio it becomes columnar dendritic, and further reduction of G by R ratio makes the microstructure more random because it makes it in the form of equiax dendritic. Okay. So, here the case shown in case of first layer microstructure formation of the laser powder bed fusion processed nickel based superalloy, it shows the microstructure akin to columnar dendritic microstructure. Okay. So, you can see that these are basically the primary dendritic arms and that is I mean primary dendrites, primary arms of the dendrite, and these are basically the secondary arms of the dendrites. Okay. So, secondary arms, and we also I mean we have not only the simulated the microstructure, we have made the quantitative study about the I mean effect of thermal gradient and cooling rate on the several microstructural parameters. For example, I mean the evolution of the primary dendrite arm spacing, which is the difference between the center line of the two I mean neighboring dendrites, okay. And then also we have evaluated the evolution of secondary dendrite arm spacing I mean in case of different microstructural feature, I mean different thermal gradient and cooling condition. So, so for your understanding, I am also drawing here the secondary arm spacings, which will be like this. So, between the neighboring two secondary arms of the dendrite, you will basically measure the SDA, secondary dendrite arm spacing. Okay. So, as we have discussed earlier also in case of casting, so as your cooling rate goes high, your SDAS goes down, and that also I mean points towards I mean lesser SDAS points towards enhanced mechanical property of the I mean deposited build sample. Okay. So, here niobium has a lower solubility in the primary phase, that means the gamma phase, which is rich with nickel because it is nickel based superalloy, and has higher weight fraction in secondary phases like lavase and delta phase. So, enrichment of niobium in the interdendritic region shows the presence of secondary phases. Okay. So, yeah, and also here the solid liquid interface, dendrite core all are marked in this typical example. So, here I mean this is the presence of secondary phases in the interdendritic region. So, this is a second example is shown in case of a classic aluminum I mean silicon alloy. So, you can see that the segregation of solutal silicon in the interdendritic I mean arm spacing, that means you see. So, here these are basically the secondary arms. Okay. So, secondary arms and yeah, so this is basically the primary arm of the dendrite, and you see that between neighboring secondary arms there is a distribution I mean segregation of silicon. So, so one thing you need to understand here, as the G by R ratio goes down, the cooling rate also goes up, and also it also causes higher rejection of solutal I mean elements. For example, in this particular example, it is the solutal silicon, and that causes distribution of solutal silicon in the interdendritic spacing. So, that is what is observed over here. Okay. So, yeah, so this is I mean so now if we I mean discuss little more about the I mean simulation outcomes. So, I mean so you see that this is a typical I mean simulated micrograph is shown for the I mean for two layers. So, earlier we have discussed the microstructure for the single layer alone, and so here we are discussing about the I mean first layer and also the second layer. So, you see that end of solidification in first layer it is should be the starting point from second layer, but that does not happen. Why? Because when the laser beam, when the powder bed is deposited and then the laser beam starts I mean melting it. So, then there has to be a remelting up to a certain depth from the I mean from the the initially solidified I mean metal in the first layer. So, that is called the remelt zone, and that remelt zone is basically shows significant difference microstructural feature than the I mean both the layer I mean first layer and also the I mean second layer. So, so then so then the solidification in the second layer does not start from the initial boundary of the first layer, rather it starts from the from the remelt zone, and then the from remelt zone the dendrites, or the secondary arms which are favorably oriented, they grow epitaxially in the second layer. So, we see the case of epitaxial growth. Okay. So, where it is also the angle of the the direction of the of the evolving dendrite trunks with respect to the direction of the maximum thermal gradient, the angle that is made by the evolving dendrites. For example, so here the direction of the thermal gradient is vertical direction, and then this is the direction of the growth of the evolving dendrite trunks. So, you see that here although in the first layer it is mostly columnar dendritic structure, okay, that we have discussed in the previous slide also, while it is going in the second layer, you do not see the formation of secondary dendrite arms. So, the microstructure is going towards cellular dendritic. Okay. So, that points towards higher thermal gradient and higher G by R ratio. So, you can see how in additive manufacturing the microstructure can vary layer by layer, microstructure can vary with the change of the laser scanning speed, and also the scanning strategy, and also the laser power intensity. So, there are so many variables, and that is why the role of process modeling is comes in a big way in case of additive manufacturing compared to even other manufacturing processes, because it will give the insight into the physics of the process, and also it can be very much useful as a process control tool, so that it can helps in achieving the desired quality characteristic of the material. Okay. So, here the angle I was discussing earlier. So, it is basically the angle between the maximum direction of maximum thermal gradient and the direction of growth axis of the evolving dendrite trunks. It is called the misorientation angle. So, as the misorientation angle decreases, the microstructure goes towards single crystalline microstructure. Okay. So, you can so from here you can very easily understand that directional solidification is what is possible in case of additive manufacturing, and it is also possible to develop single crystal microstructure by additive manufacturing with proper care and control. Okay. So, yeah, so this is here you can see the magnified view of the remelt region, that means like a buffer region between the first layer, that is the first layer of the deposit, first layer of the build, and the second layer of the build. Okay. So, you can see that here segregation of elements is more, and also there is a transition happens here between the microstructures, where from it is basically transitions from columnar dendritic to cellular dendritic. It is also possible to see the transition from columnar to equiax to columnar based on the local thermal gradient by solidification growth rate velocity ratio, and also due to the cooling rate. So, that is why it is highly dynamic and transient in case of additive manufacturing, and that also affects the microstructure formation. So, the effect of remelting and growth. So, as the depth of the melt pool reaches to a certain depth of the first layer, solidification starts from the first layer, and therefore, a coupling between the first and second layer is established during formation of the second layer. That is what I explained. So, the remelting causes redistribution of solutes and therefore, influences the secondary phase nucleation. Third takeaway is the multiple heating effect experienced by different layers during layer by layer growth process results in enhancement of secondary phases, which improves the mechanical characteristics of the fabricated material. So, what does it mean? So, you can understand that if when the subsequent layers are getting deposited. So, this is first layer, second layer, third layer. So, you can see that when the second layer gets deposited, up to a certain depth of the first layer experiences remelting. remelting, but when the third layer gets deposited, then first layer does not experience remelting at all. However, it undergoes a a homogenizing effect, because the temperature goes higher, even higher than the recrystallization temperature, and that causes change of the grain morphology, and also it causes precipitation, dissolution and reformation of precipitates, and also alters their size and morphology. So, so that means, the fourth takeaway is the grain growth in the second layer is influenced by the grain morphology of the first layer, and equiaxed grains can form in front of the columnar grains. However, due to remelting, the equiaxed grains mostly disappear and columnar grains dominate in the microstructure. Okay. So, so the prediction of the thermal conditions within the melt pool, such as temperature gradient, temperature thermal history as functions of time, cooling rate, rate of solidification, etc. during additive manufacturing process is one of the key aspects for microstructure modeling in additive manufacturing process. The temperature evolution within the system is controlled by the moving heat source as well as the latent heat release during solidification. So, during movement of the heat source, the different layers experience transient thermal conditions, that is what I discussed in the previous slide. So, which notably affects the morphology in different layers. Therefore, it is not recommended to use constant values of temperature gradient and cooling rate to accurately simulate the microstructure evolution in AM process. So, this is here you can see there is a very much difference, that often even in case of casting we generally consider the constant cooling rate and temperature gradient, which is impossible and highly inaccurate to be considered for microstructure evolution in case of additive manufacturing, metal additive manufacturing. So, so in this the case study of our research that is shown here, detail can be found in the recent publication that is going to come soon in the advanced theory and simulations. So, it is a respected journal, you can go into the detail of it if you are interested. So, so what we did, we basically used Rosenthal equation for the giving the thermal temperature distribution in the domain. Now, presently the efforts are underway to couple the phase field model with the CFD based process model that we are developing, because in that case the CFD based process model can predict the temperature distribution within the melt pool, and that temperature distribution can be utilized by the phase field model to predict the microstructure evolution in the region. So, this is a typical form of the Rosenthal equation that has been used in our work. So, according to Rosenthal equation, the temperature in the melt pool in laser melting process is dependent on laser characteristics such as laser power, scanning velocity, material properties such as thermal conductivity, heat diffusivity, absorption coefficients, etc. So, here so T is equal to T0, T0 is the temperature of the substrate, P is the laser power, and K is the thermal conductivity, and V is the scanning velocity of the laser, delta delta is the this heat diffusivity, and alpha is the absorption coefficient. So, and y is equal to y0 minus Vt. So, here we are talking about this y. So, it represents the moving frame with respect to the laser source, and here capital R is equal to root over zt minus z whole square plus y square. It represents the distance of a point on the simulation domain from the laser source. So, in the equation for R, zt represents the z coordinate of the top surface of the simulation domain, which is shown over here. Okay. So, with this we are done with the our microstructure modeling aspects of laser powder bed fusion based additive manufacturing. So, we will meet in the next class with the new module. Thank you.